So what I want to do in this video is I want to do a definite integral using the residue theorem. And this is one of the main applications of the residue theorem in evaluating lots of integrals. So there's going to be lots of big ideas that we'll kind of throw around here, but hopefully these ideas are going to be general enough that you can kind of generalize everything that we're going to say here. So what I want to do is I want to compute the real integral of x squared over 1 plus x to the fourth dx. Okay, so I want to look at this integral x squared over 1 plus x to the fourth dx. And so there's going to be a few different ways that we can think about this, but I think the best way to think about this is that since the integrand is even, you can think about this as, say, 2 times the integral from 0 to infinity. Or you can just think about this as kind of the symmetric integrals. R goes to infinity of the integral of negative r to r x squared over 1 plus x to the fourth dx. Okay, what I just said is not trivial, even if it looks trivial. Of course, if r goes to infinity, then this integral should be equal to that one. But I actually just stumbled on what's called the principal value of an integral, or sometimes the Cauchy principal value of an integral. And for example, you could convince yourself that the principal value of an integral, if you were to say the integral from negative infinity to infinity of 1 over x cubed is 0, even though that integral, strictly speaking, is undefined, because the integral near 0 is going to blow up way too fast for it to have a finite area. But even still, the principal value would be 0. So there's a little bit of analysis that I'm sweeping under the rug here. But because the integrand is even, we can do this. We could think of this as the limit as r goes to infinity of this integral from negative r to r. Or if you're bothered by that and you don't want to think too carefully about this, you could just think about this as twice the integral from 0 to infinity. Okay, I'm going to go back and do what I was doing before, this integral from negative r to r. Anyways, so what we're going to do to compute this integral is we're going to think about integrating the function. So I want to think about integrating the function f over some region gamma, where f is, you guessed it, z squared over 1 plus e to the fourth. And then gamma can be really any region that you want that has this negative r to r part of it. So you could integrate, say, over a rectangle where you integrate from negative r to r. The problem with that is that that's going to be actually a little bit tricky just based on this integral. And so part of the art of evaluating real integrals with the residue theorem is figuring out what's the right path that you want to integrate over. And it turns out that the right path for us is going to be the integral from negative r to r. So I'm just going to trace it out in red. So we're going to go that way, and then we're going to travel backwards. This will be a closed path, and we're going to travel across the circle of radius r. Okay, and so let's call this gamma 1 and gamma 2. And then gamma is going to be if we travel along both of those curves. So here it's again, it's not a smooth curve, but it's piecewise smooth. It's made up of two pieces that are both smooth, and then everything here is fine. Now, to compute this integral over gamma is where the residue theorem comes in. So we know that the integral over gamma of f, yeah, that's fine, of f is going to be 2 pi I times the sum of the residues. And so this is going to be the residue of f at, let's see, what are the zeros of our denominator that are inside the contour here? Z to the fourth equals negative 1 is going to be at e to the pi I over 4 and e to the 3 pi I over 4. So I'm thinking about if you had a circle of radius 1, this is going to be at 45 degrees, 135 degrees, and then these two I don't care about on the bottom. I just care about these two values there. Okay, so it's going to be the residue of f at, so again, that's e to the pi I over 4, and the residue of f at e to the 3 pi I over 4. And so that's going to be this total integral here. On the other hand, this integral can be thought of as the sum of two integrals that we'll talk about. So this is going to be, so let's first calculate what these residues are. So the residue of f at e to the pi I over 4 is just going to be a simple pole. And so what that means is we're going to be looking at, again, lots of ways to do this, but I think the easiest is just, let's look at this as, we're going to look at the limit. So residue of f at e to the pi I over 4 is going to be equal to, so it's going to be equal to the limit as z approaches e to the pi I over 4 of z minus e to the pi I over 4 times z squared over 1 plus z to the 4th. And then if we apply L'Hopital's rule here, I mean, you could factor the bottom if you want. You get z squared plus or minus I as the factors, and then each of those factor. Yeah, that's fine. But this is also fine. So you get, let's see, as z approaches e to the pi I. So we're going to get the limit as z approaches e to the pi I over 4 of 4z cubed in the denominator. So that means that we only apply L'Hopital's rule once. And then the derivative of the numerator is going to end up being z squared plus 2z times z minus e to the pi I over 4. And so that term is going to go to 0. We end up with 1 over 4 e to the pi I over 4. So that's 1/4 e to the negative pi I over 4. Likewise, the residue of f at e to the 3 pi I over 4. So this is going to be very similar. This will turn out to be, so this will turn out to be 1 over 4 e to the 3 pi I over 4. And so that's going to end up being 1/4 e to the minus 5 pi over 4. E to the positive 5 pi over 4. There we go. Yeah, e to the 5 pi over 4. Okay, so that's got to be the residue there. Yeah, that's fine. And that's going to be, so when I said e to the negative pi over 4 before, I meant e to the 7 pi over 4. So what I said was right, just not helpful. It doesn't matter. Anyways, this is fine. So the entire integral over f is going to end up being 2 pi I times the sum of these residues. So e to the 5 pi I over 4 plus 1/4 e to the 7 pi I over 4. And so that's going to turn out to be, what are those? That's going to turn out to be, we can factor out an e to the 5 pi over 4. So that's going to be multiplied by 1 plus e to the pi I over 2. No, e to the pi I. No, pi I over 2, because it's 2/4. And so that's going to end up being pi I over 2 times e to the 5 pi I over 4, which we'll figure out in a second. Okay, so I guess we might as well figure that out now. So that's cosine of 5 pi over 4 plus I times sine of pi over 4, all times 1 plus e to the pi I over 2, so that's I. Okay, now cosine of 5 pi over 4 and sine of 5 pi over 4 are the same. want to make sure I'm not missing anything here. I inadvertently made our lives difficult by simplifying what we had. So this is going to be pi I over 2 times 1 plus I times cosine of 5 pi over 4. Now I'm quite unhappy with this. Anyways, we'll see where it takes us. So this is going to be negative square root of 2 over 2 minus I times square root of 2 over 2. We can certainly factor out the square root of 2 over 2 bit. And then we're going to be left with 1 plus I times negative 1 minus I. So that's pi I over 2 times negative 1 times 1 plus I quantity squared. 1 plus I squared is going to be just 2I. So we're getting there. I think I made our lives too difficult by trying to simplify before, but oh well. So this is going to be 2I. And then let's see, this 2 will cancel with that 2. I squared is going to be negative 1, so that cancels with that. And we end up with this integral being equal to pi times square root of 2 over 2. Okay, so let me just take a step back here. Using the residue theorem, this integral is going to end up being 2 times, so this is going to be pi divided by square root of 2. Let's just write it like that. So that's pi over square root of 2. So that's the integral involving the residue theorem. And now the integral that we're going to evaluate, we're going to look at in 2 ways. So we're going to also evaluate this integral of f, over our region gamma that we defined as the integral over gamma 1 plus the integral over gamma 2. And we'll just have to do these kind of by hand. Now, these are not closed paths. The residue theorem doesn't apply. We're just going to have to go back and think about what are these integrals. But if you think about gamma 1, so sorry to scroll, but gamma 1 is exactly the integral that we're looking for, because we're trying to evaluate z squared over 1 plus z to the 4th along the real axis as we go from negative r to r. That's exactly what this is. So the integral over gamma 1 is going to turn out to be exactly this integral. And then all we have to do is evaluate the integral over gamma 2, subtract them, and then this will give us our answer for the integral over gamma 1. Okay, so this is really, just to put this in perspective, this is the limit as r goes to infinity of the integral of our function f over gamma 1. Okay, that's what we're looking for. And then we know that if we add these up, so let me just say what we did here. So basically what this tells us is that the integral over gamma 1, which is the integral that we're looking for, is the integral of f, which is pi over square root of 2, minus the integral over gamma 2 of f. And then we're going to let r go to infinity, and then we'll recover the integral that we were looking for, and that'll be our answer. So there we go. Notice that this pi over square root of 2 is independent of r, so as we let r go to infinity, that'll be the same. So we really just have to think about what's going to happen to f of z as r goes to infinity. And so that's what we'll do next. So we're going to turn to that. So next, we're going to look at the integral over gamma 2 of z squared over 1 plus z to the 4th dz. And so let's think about what that's going to be. This is going to be equal to, we're traveling along a circle of radius r centered at the origin, traveling counterclockwise. So this is going to be the integral from 0 to pi. Our gamma 2, by the way, is going to be r e to the it as t goes from 0 to pi. So this is going to be r squared e to the I, e to the 2it over 1 plus r to the 4th e to the 4it times the derivative times gamma prime. Let's not forget that. So that's going to be I r e to the it dt. Okay, and so we could evaluate this integral if we wanted to. Just kidding. We probably can't. Maybe we can, but it doesn't matter. All that we really need to do is bound it. So now, notice that if we bound this integral, so the z squared over 1 plus z to the fourth dz, this is going to be less than or equal to, let's think about this. This is going to be less than or equal to pi, actually it's pi r, the length of the curve, times the maximum. So this is going to be times, let's see, r cubed over 1 plus r to the fourth, which I'm not happy about. No, I'm doing too many things here. Sorry. Doing too many things. I went off my notes a while back and now I'm, all right. Yeah, all we need to do is bound it. So this is going to be less than or equal to the length of gamma 2 times the maximum value of the modulus of z squared over the modulus of 1 plus z to the fourth, as z is in a circle of radius, as z is in gamma 2. Okay, and so this maximum is going to turn out to be, let's think about this. So the maximum, so the length of gamma is easy. That's, you get 2 pi r, but it's only half of it, so that's just pi r. And the magnitude of z is also easy. That's going to be just r squared. And the magnitude of 1 plus z to the fourth, so the magnitude of 1 plus z to the fourth by the reverse triangle inequality should be greater than or equal to the magnitude of 1 plus, I need to think about this. Yeah, let's do it this way, because I always forget the triangle inequality. I never memorize the things I don't need to memorize, and sometimes it shows, but that's fine. So z to the fourth is just r to the fourth. And so this is going to be z to the fourth plus 1 minus 1. And that's less than or equal to the modulus of z to the fourth plus 1 plus 1. And so that tells you, there we go. So the modulus of z to the fourth plus 1 is greater than or equal to r to the fourth minus 1. And therefore, when you take reciprocals, the inequality flips. We get that this is less than or equal to r to the fourth minus 1. The point is that this is pi r cubed over r to the fourth, basically. And so that's the value. And so as r goes to infinity, so notice that as r goes to infinity, this integral over gamma 2 of z squared over 1 plus z to the fourth, notice we didn't even actually evaluate it, but whatever it is, this is going to go to 0, because this is bounded by something like 1 over r. And so that integral is going to go to 0. And so what that tells us is that this integral from negative infinity to infinity of x squared over 1 plus x to the fourth, which was equal to the limit as r goes to infinity of the integral from negative r to r of the same integrand, which was equal to this integral as r goes to infinity of this complex integral, which we call gamma 1 of z squared over 1 plus z to the fourth, which was equal to the integral over gamma, which we said was pi over square root of 2, minus the integral over gamma 1, so z squared over 1 plus e to the fourth dz. And then we just finished by saying that as r goes to infinity, this integral goes to 0. So this integral is going to go to 0, and we end up with pi over square root of 2. So it's this really weird quirk where we have these real integrals, and the easiest way to evaluate them is with complex machinery, complex analysis. Okay, so that's that integral. That's how the residue theorem can be used in real life to evaluate real integrals.